All right, welcome to The Explainer. Today, we're basically going to be detectives, solving a really cool linear algebra mystery, and we're going to see how just one tiny clue can completely unravel a whole web of complex equations.
You know, it's like something out of a classic detective story, right? We've got a bunch of unknowns, this complicated network of connections, and just one small, seemingly simple fact. Our job is to take that single piece of information and use it to blow the entire case wide open.
So let's set the scene for our little mystery. Imagine we have two different mathematical worlds, which we call vector spaces. We'll call our starting point V and our destination W. And the bridge that connects them? That's a special kind of map, a linear transformation that we'll call T.
Okay, so here are the facts of the case laid out for you. Our two spaces, V and W, they're both collections of 2x2 matrices, and each one has its own set of unique building blocks, or what we call a basis. Our main person of interest, this transformation T, is the rule that dictates exactly how a matrix from V gets turned into a matrix in W.
Now here's the thing about these linear transformations. You can always represent them with a matrix, and this is ours. This matrix right here describes the entire operation of T. But take a closer look. There's an unknown variable, A, just lurking inside, and that is the heart of our mystery.
And just look at that. This one little variable, A, is sprinkled in 3 different places. Its value is literally the key. It's going to completely change how this whole transformation behaves. So, our first job is crystal clear. We have got to figure out what A is.
So here's our mission. Should we choose to accept it? It's a two-parter. First, we need to unmask A, and then use that knowledge to find something called the kernel of T. Then, for part 2, we have to find the common ground between our two spaces, what we call their intersection.
Okay, so where do you even start with something like this? The main piece of evidence we have has a variable in it. It feels impossible. But deep in the case file, there is one critical, game-changing clue.
And this is it. This is the whole enchilada. The key that unlocks everything. It says that the third basis vector of our target space, W, is in the kernel of T. But what in the world does that actually mean?
So what on earth is the kernel? Think of it like a transformations black hole, or zero zone. It's this special collection of vectors from our starting point, V, that get totally wiped out by the transformation. When you apply T to them, they get sent straight to the zero vector over in W.
And this is where it all clicks into place. It's like a chain reaction, dominoes falling one after another. Check this out. 1. Because we have a non-zero vector in the kernel, we know the transformation is squashing things down to 0. 2. That means the transformation isn't a perfect reversible one-to-one mapping. It's not an isomorphism. 3. And if a transformation isn't reversible, its matrix isn't invertible. And here it is, the final crucial leap. 4. A matrix that isn't invertible always has a determinant of exactly 0. That's our smoking gun.
So that whole chain of logic? It just handed us the perfect tool for the job. We now know for a fact that the determinant of our mystery matrix has to be 0. And by setting it to 0, we can finally solve for A.
Okay, let's get our hands dirty. We start with the matrix. Now, calculating the determinant of a 3x3 can be a bit of a pain, but we can make our lives way easier by using some standard row operations to get some zeros in that first column. This totally simplifies the problem without changing the determinant's value at all.
And after all that work, after simplifying everything, that big, hairy determinant calculation, it boils down to this one beautiful, simple expression, 6a minus 12.
And since we know from our detective work that the determinant must be 0, we can set up this super simple equation. The mystery of A is just one tiny step away from being completely solved.
Boom! There it is. The mystery is solved. A has to be 2. No other possibility. And just like that, the first part of our case is closed.
Okay, so now that we've unmasked A, we can finish up the first part of our mission. We just pop that 2 back into our matrix and ask a simple question. Which vectors get turned into the 0 matrix? And the answer is any combination of this one specific matrix right here. This is the basis for our kernel.
All right, mission objective 1 is complete, but we're not done yet. Now we have to figure out the intersection of our two spaces, V and W. Basically, what do these two worlds have in common?
Now, when you're faced with a problem like this, finding the intersection, there are usually 2 paths you can take. There's let's call it the brute force method, and then there's the elegant, smarter path. Let's check them both out.
So, the long road? Oh man, it is pure brute force. You're setting up this gigantic system of equations, just grinding through algebra. It's just a mess and so easy to slip up. The elegant path, though, it uses this incredibly powerful shortcut called the dimension theorem.
So let me walk you through this elegant path. It's actually really cool. We already know the dimension of V is 3, right? And the dimension of W is also 3. Then, with a bit of calculation, we can figure out the dimension of the space they create together, which we call V plus W, is 4. Now you just plug those numbers into the formula. 3 plus 3 minus 4 equals 2. That's it. The dimension of the intersection has to be 2, which tells us we only need to find 2 independent vectors to define that entire common ground.
So now we just have to find our 2 vectors. And guess what? We've already got one of them. That vector we found for the kernel? Yep, that's in the intersection. And for the second one, we can just take a close look at our original basis vectors. Turns out, B1, one of V's basis vectors, can also be built using the basis vectors for W. And since these 2 vectors are independent, they are the perfect basis for our 2-dimensional intersection. Case closed.
So let's just step back for a second. What's the real takeaway here? The crucial thing to see is that we didn't solve this problem by just being a calculator. The real breakthrough came from understanding a deep core concept. That single clue about the kernel let us figure out the determinant was 0, which gave us A, which led us to the kernel's basis, which then helped us find the intersection. It was the one thread that let us unravel the entire sweater.
And that really makes you think, doesn't it? We tend to think of the kernel as just, the stuff that gets squashed to 0. But today, we saw it's so much more. It held the secret to the entire transformation. So you have to wonder, what other deep, powerful secrets are hiding inside the kernel? Just waiting for us to ask the right question.